This video might be a little longer, so bear with me. So the contents of this video are as follows. First of all, we'll know what is moment of inertia tensor. Okay, and we know what is moment of inertia already, but here we'll study about the moment of inertia tensor and its derivation also. After that, we'll see how it transforms for different frame of reference, and then we'll know about the parallel axis theorem and the perpendicular axis theorem. We know moment of inertia is denoted by I, and it is given by mass times distance square. Now we are going to see in terms of tensor. Okay, so we can derive moment of inertia tensor from the angular momentum, which is given by L as R cross P, where P is the linear momentum and it is given by mv. We can write also summation of mv. Okay, so we'll replace it r cross m v, where v is a vector. Now as m is a constant, so I can take it out and write r cross v. Now here this v is a summation of translation plus rotational motion. Okay, so I can write is the translational velocity and the rotational velocity is given by omega cross r. Okay, so now I can put these things here, summation of m r cross u plus omega cross r. Now I'll simply break this bracket, so I can write r cross u plus r cross omega cross r. We'll leave the first term as it is, plus. Now this term is a vector triple product, so we can write the vector triple product as a cross b cross c can be written as b a dot c minus c a dot b. So it is also known as back cap, it is back, it is cap. So we'll break it like this. Okay, now I can take r out, then I can write omega dot. Now we just simply multiply this m cross u and summation of m omega r square minus r dot omega. Now for ith particle I can write Li, and it is going to be summation of m r cross u plus summation of m. Now here I am writing it for ith particle, so I will write the velocity of ith particle. Okay, now here it is r square minus ri. Now since I have written ri, I can't write again ri, so I will write rj, and since I have already written omega I will write it as omega j. Now I can write this m as the mass of the body, because it is a summation of all the mass. Okay, so I can write it as capital M, which is the mass of the body. Okay, and I can write this r to be the rcm, which is the center of mass. Okay, it is the distance of the center of mass cross u plus summation of m. Now I can write it as r square, and I can change the omega I to omega j, and I can write it del ij, which is the Kronecker delta. Okay, so it will be omega I. Okay, now we have ri, rj and omega j, so that we can take out the omega out from the bracket. Now I can take the r out, rcm cross mu. Okay, plus summation m r square del ij minus ri and rj. Omega j is out. Okay, now here this term, okay, let me highlight it. This term is called as moment of inertia. Ij to be summation of m r square del ij minus ri rj. So that is the formula for moment of inertia. Okay, we'll write the moment of inertia tensor. So it is given by I, then it is first term will be ixx, the second term will be ixy, and the third term will be ixz. Okay, similarly I can write it as iyx, iyy, and iyz, and izx, izy, and izz. Okay, so now we'll find out the diagonal elements first, then we'll find out the off diagonal elements. So we have the formula for moment of inertia, so we will use this and find out the elements. So first of all I will find ixx, so I will put x in place of I and x in place of j, so we will get summation of m, then r square and del of x, so it will be 1 obviously. Now r of x and r of x, so I can write now this thing will be 1 because these are same. If it was different xy, then it will be 0. So summation of m r square minus rx square. Now r square can be broken into its components such as rx square plus ry square plus rz square minus rx square. So now this thing will be cancelled out and will remain with this. So this is the xx component. Now I am not gonna derive the yy and zz because they will be similar. Okay, so let me write them. Iyy can be written as summation of m r of z square plus x square, and izz can be written as summation of m r of x square plus summation of plus r of y square. Now the trick of writing this is when there will be xx, okay, so the next term will be y and z, so it will be summation of y and z. Similarly when you use r of y, so we will have the next two terms, that is z and x, and for zz it is also the same, it will be the summation of x and y. Okay, now we'll find out the off diagonal elements. These three are the diagonal elements. Okay, now you see we find out these things. Now we have to find out these three things. Let me use a different color. So we'll find out these three things, and if we find these three will be automatically found out. Now let's try for ixy. So I can write it as summation of m, then I will have, there is our r square, then del of x of y minus r of x, r of y. Okay, now since it has two different terms, so this thing is going to be 0, so the whole term is going to be 0, so I can write it as minus summation of m r of x, r of y. Okay, now similarly I can write it for y, z and zx, so there will be like summation of m r of y, r of z minus summation of m r of z, r of x. Okay, now they are same as y, x, it is same as zy, and it is same as xz. Okay, because if you just break it out, there will be y in place of x and x in place of y. Now since they are commutative, so it will be the same. Okay, if you have confusion, let me clear it by doing this. Okay, so I can write it as summation of m, then similarly r square del of, it will be yx minus r of y r of x. Okay, this term is 0, so I basically left with minus of m r of y r of x, which is nothing but equal to summation of m r of x and r of y. This term is same as this term, so I can say ixy is same as iyx. Similarly, iyz is same as izy, and izx is same as ixz. Okay, so by now we get all the elements of the tensor matrix, sorry, it is not matrix. Tensor is not a matrix. Okay, just let me write the tensor first, then it will be easier to put the values xy. Then I have I of x of z. So we will now put the values. Okay, so first of all we have ixx. So ixx has a value of summation of m, and we can remember it as, since it is x, so it will be summation of the next two terms. So it will be r of y square plus r of z square. Okay, so similarly I can write the next diagonal term, actually iyy. It will be nothing but equal to summation of m r of z square plus r of x square. Okay, in the last term remaining will be summation of m r of x square plus r of y square. Okay, or you can actually, I can also write in place of just wait, in place of r of y you can also write directly y. In place of r of z you can also write z, because r of z means it is z, because r is what, r is nothing but it is a vector, and it is consisting of what, plus z of k cap. Okay, r can be written in terms of its components. So r of y, if I write r of y, it means it is these things. Okay, if I write r of y, simple. Okay, so we got the diagonal elements. Now we'll write the off diagonal elements. So we'll write first I of xy. So I of xy can be written as minus of summation of m r of x and r of y. Okay, similarly I can write I of xz as summation of m r of x and r of z. Okay, so now we'll write I of yz, so it can be written as minus of summation of m r of y and r of z. Okay, so similarly let me write the other ones. So finally we got the moment of inertia tensor, and I can also write it in terms of x and y if r of y and r of z makes a little bit of confusion. So we will write it simply as I. So first we'll write the diagonal element. Summation of m ixx can be given as y square plus of z square. Yeah. Then I will write minus of summation of m. Then it will be xy. Okay, so it is the moment of inertia tensor. So this thing is our moment of inertia tensor. In transformation of moment of inertia tensor, we study how the moment of inertia tensor changes when we change the body frame. Now for studying this, we consider a point P in a body frame O. Okay, now the point P is fixed at this position. We will not change the position of the point P. Rather, we will do what? We will change the position of the body frame O to O dash. So let it be a new body frame O dash, and this is translated through a distance of a. Let it be shifted through a distance of a. Now the point P is fixed here, so we will find a new position vector with respect to O dash. So let me join this and we'll get a new position vector. Let it be R dash. Okay, so this thing is R dash and this thing is R. So this is R and this is R dash. Okay, so now with respect to O, I can write the moment of inertia tensor, and with respect to O dash, I can write the moment of tensor to be I dash. So we'll write this thing, right? So the moment of inertia tensor with respect to O, I can write it as I. So I will nothing but is equal to what? Summation of M R square del of I del of J minus of Ri and Rj. And I can write the moment of inertia tensor let it not call tensor, let it call moment of inertia just. Okay, let it be moment of inertia with respect to O, because I am not writing the whole tensor. Now the moment of inertia with respect to O dash, I can write, let it be I dash. So I can write it as summation of M, it will be now R dash, as the position vector is changed. So I write it as R dash square del Ij minus Ri dash and Rj dash. Okay, let it be 1 and this thing be 2. Now you see, if I look closely, you see this is the first position vector, this is the translation vector, and this is the second position vector with respect to O dash. So I can use triangle law of vector addition here. So from this, by using triangle law of vector addition, I can write R to be R dash plus A, and I can write R dash to be R minus A. Simple? Look simple? So now I will put the value of R dash in equation 2. So equation 2 implies I dash to be summation of M R minus of A whole square on del Ij minus R minus of A R minus of, it will be Ri, it will be Ai. Now you see it is a complete vector, but they are the component of the vector. Okay, so I will write Ri minus Ra and Rj minus Az. Clear? Now I will break this out and let's see what happens. Summation of M, if I just break it out, I will get R square minus twice of Ra plus A square to del of Ij minus Ri minus Ri Az minus Ai Rj plus Ai Az. Okay, so moving forward, now you see it is let me change the color. You see this term is R square del Ij and Ri Rj. I can write them to be the moment of inertia tensor. I can write because summation of M is here, and R square you see here R square del Ij and Ri Rj, they are same. Okay, so I will write it accordingly so that I can write it as the moment of inertia tensor. Okay, so I will break it up. So it will be summation of M R square del Ij minus Ri Rj plus summation of m. Then I can take common this thing and this thing, so I will write it as del a square del ij minus ai is a. Okay, now the remaining term, I will write the remaining term. So what are remaining? So the remaining terms are this term, this and this term. Okay, because rest of them I have covered, so let's write them. Plus summation of m ri aj plus ai rj minus twice of Ra del of ij. So I can write this term as our moment of inertia I. So I will write it as I plus summation of m square del of ij minus of ai is a plus. Now this is the summation of m, so I can write the mass for the whole body. So I can write it as capital M. Okay, so I will write it as capital M. Now this is Ri, so I can write Ri to be the capital R. Will write it as RCM. AZ will be as AZ. Then why I am pronouncing them wrong? It is AI. Okay. Then RJ I will write RCM. Similarly for this I will write it at RCM A and del IJ. Now for simplicity we consider the axis passing through the center of mass. Okay, we consider the axis to be passing through the center of mass. The axis is passing through the center of mass, so the distance of the axis from the center of mass is 0. So I can write RCM to be 0. Now if the RCM is 0, you see this term will just vanish, RCM and RCM. So as a whole this term will be 0. Okay, as a whole this term will be 0. So what we are left with, I can write now I dash to be equal to I plus summation of m a square del ij minus ai and aj, because this term is 0, this term is equal to 0. Why? Because we are considering the axis passing through the center of mass, so the distance becomes 0, this becomes 0 and this also becomes 0. So as a whole this term becomes 0, so we are left with this thing. So this is the transformation of the moment of inertia from two different frame of reference with respect to two different frame of reference. Let me highlight it. The formula required. Now by using this formula we will write the parallel axis theorem and the perpendicular axis theorem, which are the last topic of the video, by the way. So now we are gonna see the parallel axis theorem and the perpendicular axis theorem. So first, parallel axis theorem. So this theorem states that the moment of inertia of a body about any axis is equal to the moment of inertia about an axis passing through the center of mass plus the product of mass of the body and the distance between the two axes. Now that is a quite linguistic definition. Now let's see what does it physically mean. Okay, now for understanding this we consider a situation where A is a body and xy is the axis which is passing through the center of mass of the body. Okay, so the moment of inertia about the axis xy is ICM. Now we consider another axis which is passing through the body and is parallel to the axis xy, that is which is passing through the center of mass. Distance between the two axes is given A and the mass of the body is m. We have to find out the moment of inertia about this axis. This is unknown. Okay, now according to the parallel axis theorem I can write the moment of inertia of the body about x dash and y dash axis which is passing through the body and is parallel to the axis x dash and x and y. So I can write it to be the moment of inertia about the center of mass plus mass of the body into the distance between the two axes square. Okay, so this is the this is what the parallel axis theorem is trying to tell us. That is, I unknown is equal to ICM plus m a square, where m is the mass of the body and a is the distance between the two axes. Now we are going to prove this relation using the transformation of the moment of inertia tensor. That is, using this relation we can prove this parallel axis theorem. Okay, now how we will see it? Now we consider the transformation to be in the x direction, so that this shift is in x direction. So I can write it, I can write the position to be a, 0 and 0, because it has moved in x direction only, so there is no y and z component. So I can write it a, 0, 0. Okay, now we see. Now from the transformation relation, you can see this is the transformation relation. Now we can use this relation to prove the parallel axis theorem. So we will use this transformation relation to prove this thing. So let's write the transformation equation first. We have from the transformation relation I dash to be equal to I plus summation of m a square del I is a minus ai is a. Okay, so you see it is moved in x direction only, so the x component only present, that is a only present, and rest are 0. So I will write this in component form, that is ixx and iyy and izz. So in ixx I can write it to be I dash xx plus ixx plus summation of m. Now in x-axis, okay, in x-axis the component of a vector is a only. Del ii is equal to 1, you know, so I can write del xx to be equal to 1. So I'll write it a square minus a. So this term is 0, so I can write it as axx. Now for iyy I can write it as iyy plus summation of m into a square minus, now you see there is no y component, so it is 0, so it becomes iyy plus summation of m a square. Similarly, izz dash can be written as izz plus summation of m a square. Now which is the parallel axis theorem? We already have seen this thing, that we already have seen this thing. We can write the unknown moment of inertia in terms of the known plus the summation of mass times the distance square between, and a is the distance between the two axes. Okay, simple. Now if it is moving in x direction, in that direction the moment of inertia is same as that of the center of mass, and there is no x and there is no other term actually. Okay, so this is what the parallel axis theorem. Let me summarize this. So I can write according to ixx is equal to ixx, I dash yy is equal to iyy plus summation of m a square izz is izz plus summation of m a square, where a is the distance between the two axes. Simple. So the last topic of the video, the perpendicular axis theorem. So it states that for a thin laminar body Now we will understand what is a thin laminar body. So for a thin laminar body, the moment of inertia about an axis perpendicular to the plane of the body is equal to the sum of the moment of inertia about the other two axes. Okay, now what does it mean actually? So let's consider again our body, or let it be A. So the moment of inertia about a axis perpendicular to the plane of the body, so let it be IZZ. Okay, so it is perpendicular to the plane of the body. Oh wait, thin laminar body. So what does a thin laminar body means? Now for a, let's consider this body to be a thin laminar body. So for a thin laminar body, the thickness is negligible as compared to the other dimension. That is, we can neglect the thickness. Okay, so the thickness of the body can be neglected as compared to other two dimensions, that is the length and the breadth. So we can neglect the thickness. So that is a thin laminar body. Now for a thin laminar body, the moment of inertia perpendicular to the plane of the body, that is IZZ, can be written as the sum of the moment of inertia about IYY and IXX. That means I can write IZZ to be equal to IXX plus IYY. That is, the moment of inertia about the axis Z is equal to the moment of inertia about the axis Y and X. Okay, so we'll see the proof of this. Now that is a condition, that is a required condition. Laminar body, thin laminar body, that is a required condition. It will be necessary again in the proof. So let's start the proof. So we have I can write IZZ as summation of M. Since it is Z, it will be X square plus Y square. Okay, again I can write IYY to be the summation of M Z square plus X square, and some IXX can be written as summation of M Y square plus Z square. Okay, I can add this to be 1, it is 2, and it is 3. 1, 2, and 3. So I can add 2 and 3. Adding 2 and 3. Adding equation 2 and 3. I can add that is IYY plus IXX is equal to summation of M can be taken common, so it will be Z square plus X square plus Y square plus Z square. So I can add summation of M. It will be twice of Z square plus X square plus Y square. Okay, now for IZZ, it is nothing but a summation of M X square plus Y square. Now there is an extra term, YZ square. Okay, so we have considered the body to be thin laminar. Okay, so we can neglect the thickness, there is a Z component can be neglected. So it is a thickness, so we can neglect this. So if we just say it to be 0 because it is negligible, it is a thin body, it is negligible. So I can write it as summation of M X square plus Y square, which is nothing but is equal to IZZ. That means I can write IZZ to be the sum of IXX plus IYY. So that is what the perpendicular axis theorem states, isn't it? So this is the perpendicular axis theorem, and by this we have successfully completed all the 3 contents, and it is a very lengthy video after all. So thank you for watching, and I will attach this whole PDF in the description. So if anyone need, you can collect it from the description. Thank you. I will see you in the next